All right, we're going to do some conversions from a velocity time graph to position time and acceleration time graph here. And we're going to assume in all of these that each one here is representing 1 unit or 1 meters in this case for position time, 1 meters per second, and 1 meters per second squared each one of these, and that the time is in seconds. Okay, first, I find it easiest to go from velocity time to acceleration time. First, in this particular case, we have to find rise over run, or the slope, in order to get the acceleration, and the acceleration is constant throughout this whole region. So let's see. In this one, actually, we can also change the units as well, but I'll just keep it the same. The slope here, the rise is 2, the run is 4 for the first region. So that's 2 divided by 4, which is a half. So my acceleration is positive half for the first 3 seconds. And then the slope in this region is a straight horizontal line. It's just 0. So for the next seconds, it's 0. And they are connected using, it's hard to see because it's not zoomed in enough, but just dotted lines. And that's it. So if you want to show your work for this, you can just simply say that the acceleration from 0 to 3 seconds will equal to the rise over run, which is 2 over 4, or 0.5. And the acceleration from 3 to 6 seconds is going to equal to just 0, because it's a straight horizontal line. At this point, I assume that you folks are good enough with slopes that if it's horizontal right away, you can recognize that it's 0. Now, in the graph here, we need to draw the position time graph. In order to do that, we need to find the displacements at different regions. So let's do that. So we can find the displacement from 0 to 3 seconds, and we can find the displacement from 3 to 6 seconds. From 0 to 3 seconds, we have to find the area of this triangle, and for the next section, area of this rectangle. The area of the triangle is 2 times, actually it's 4 seconds, sorry. I should say this is 4 and this is 4 to 8, and this is 0 to 4, 4 to 8. So it's 2 times 4 divided by 2, which is 4 meters in the east direction. So I'll just leave it as positive 4. And maybe I'll write it out. And this is meters per second squared. And displacement from 4 to 8 is the area from here to here. And that area is going to be just 2 times 4, which is 8 meters in the east direction. Okay, so for the position, starting position is 4 meters in the west direction. That's starting here, so negative 4. And then from 0 to 4 seconds, so after 4 seconds, 1, 2, 3, 4, we move, sorry, 1, 2, 3, 4, we displace by 4 meters in the east direction. So we go 1, 2, 3, 4 here. So I'm going to put a dot right there. And from 4 to 8, we displace again for another 8 meters. Okay, we can definitely do that. 1, 2, 3, 4 seconds. We go 1, 2, 3, 4, 5, 6, 7, and 8. So right there. Okay, how do we connect them? Well, this region over here, the velocity is constant, so I'm going to draw a straight line between these 2 points, as straight as I can. And for this section, you can see that the velocity is 0, so the slope of my position time graph right here needs to be 0. So I'll use purple to kind of indicate that. And the slope right here, well, that's the same slope as this continuous line. So I'll just draw the line, kind of connect this like this. So you can see right in the beginning, the slope here is 0, velocity is 0, and the slope is increasing to a value of 2 actually, and the slope here is 2, and that's it for my first one. Let's do the next graph. Let's use a different color to do this one. I'm gonna use pink. And we're gonna do the same idea. We're gonna do the displacement from this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 9 and this is 6. So, sorry, before the displacement, let's do the average acceleration. So I'm just going to erase this and acceleration from 0 to 6 and acceleration from 6 to 9. Okay, from 0 to 6, my rise is -3 and my run is just 6, that's -0.5. And for the next section, my rise is 0 and my run is 3, so that's 0. Units are meters per second squared, direction is east. Meters per second squared, direction is east. And that means I kind of start at a -0.5 up to the first 6 seconds, connected using a dot, and 0 for the next sections. How about displacements? So let's look at the displacement from 0 to 6 seconds and the displacement from 6 to 9 seconds. The shape here is a triangle. The height is -3 and the base is 6. We're going to divide that by 2 because it's a triangle. That's -9 meters in the east direction. And for the next one, 6 to 9, I have a square. Its height is -3 and base 3, and this is -9 as well. Let's start the position. Our starting position is 10 meters in the east direction, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way here. After 6 seconds, so 1, 2, 3, 4, 5, 6, we move we move -9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we move all the way here. Or you can just say 10 minus 9 is 1. I kind of made this a little bit. I was just counting it, but you can just do 10 minus 9, 1, and just go up by 1. And I don't need this point anymore. And once I have that, so I can also label this, it helps, 10. 10 minus 9 is just 1. And after another 3 seconds, 1, 2, 3, I go down by another 9. So that's -8. 1, 2, 3. And this is -8. Okay, we got it. Now, during this time, the velocity is constant, so I'm going to connect these using a straight line. That's pretty nice and straight. And the slope, okay, so right at the beginning, our velocity is 0, meaning that our slope here should be a horizontal line. And we know that the slope here is just like this. So connect them. Something like that. and that shows that we get a nice curve area here. You can see the slope, the steepness of the line increases as the velocity increases, and it's increasing in the negative direction. This is also in the negative direction, so it looks fantastic. We got two more examples here. I'm going to zoom in. Okay, let's look at the next two graphs, and these ones have more sections, so a little bit more work for all of them, but we can definitely do them. Let's do the average acceleration. So I'll just do a sample one, and then I'll just write the answers to them. So here we got 0, 1, 2, 3, 4 seconds, 6 seconds, 9 seconds, and 12 seconds. So average acceleration, you would have to do it from 0 to 4. You would have to do it for 4 to 6. You would have to do it 6 to 9, and from 9 to 12. And from 0 to 4, rise over and run, that's 3 over 4. And then you have 0, and then you have negative 3 over 3, which is negative 1. And then you have negative 3 over 3, which is another negative 1. So from 6 to 9 is actually exactly the same value. Putting those into perspective in our diagram, we have 3/4, so that's approximately, actually looking at our numbers, do this, no, I'll just do it like this, that's fine. So positive 3/4 for the first 4 seconds, and then we go to 0 for the next 2 seconds, and then we go to negative 1 for the rest. And that is our accelerations, and my units for all of them is meters per second squared in the east direction. I would also have to do the displacement for each one, so I'll do that here. Displacement for 0 to 4, displacement for 4 to 6, displacement from 6 to 9, and displacement from 9 to 12. And to do these, I need the area. So the area for the first part over here, that's 3 times 4 divided by 2, all positive. So 3 times 4 divided by 2, that's going to be positive 6 meters in the east direction. And then we have, for the next section over here, we have 2 times 3, that's 6. Actually, I'll write it out because it's a rectangle this time. It is 2 times 3, which is 6 meters per second. And I'll just write the 6 actually. I want the numbers in there. 6 to 9, we have a triangle. It's positive height, positive base, 3 and 3 divided by 2, that's 4.5 meters per second. And finally, for the last one, we have a triangle which is in the negative direction, so negative 3 times 3 divided by 2, which is negative 4.5 meters per second. Meters, just meters, in the east direction. So we have all of this. Let's put it all into action. Our position starts 8 meters west, so starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, we start right here. And then our first displacement is positive 6. That means that after 4 seconds, 1, 2, 3, 4, we move up by 6. So going from negative 8 to negative 2. And then we move another 6. After 2 seconds, so after 2 seconds, we move up 1, 2, 3, 4, 5, 6. And maybe I'll write some of the values. So this is -8, this is -2, this is 4. And then we go up by 4.5 after 3 seconds. So 1, 2, 3, 4.5. So that's 8.5, 4 plus 4.5. And after another 3 seconds, we come back down by 4.5. So 0.5, 1, 2, 3, 4.5. We come back to here, and we're back to position 4. How do we draw this? Well, look at constant velocity sections first. Here we got a constant velocity, meaning in this region it's a nice straight line, and that helps a lot. And then we know that at this stage and this stage, both of them, we have 0 velocity. So that means right at time 0 and then right at time 9 seconds, we have our position will be represented by a vertical line like this. And our slope at the very end here, right here, it's negative and it's pretty steep. So it will look something like this. I don't have any other information to kind of go with. So I'll just draw that like this. I already know that this is +3 and this is -3. So if this slope is the steepness here and here needs to be the same. It's just the directions that are different. So then I just connect them. So initially it's here, it kind of curves like this. Here it curves like this. Connect them. Beautiful. Here the curve is kind of like this. Connect this to this. And connect this little looking curve to this one. And it's a beautiful artwork. We're going to do the next one. We're going to do, this is 2 seconds. We got 4 seconds. We got 5 seconds. Oh, sorry, 6 seconds. And then we get 7, 8, 9, 10 seconds, and 11 seconds. Okay, a lot to do here. This is 2, and this is 4. I need a little bit more space. I'm just going to shift everything in this direction. Okay, let's do accelerations. And we're going to do 0 to 4. Acceleration, sorry, to 2. 2 to 4. 4 to 6. 6 to 10. Acceleration 10 to 11. Equals, 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 and equals. And I need the arrow. Okay, the slopes. The first slope is 1/2. So that's 0.5 meters per second squared in the east direction. The next one, the slope is 0 meters per second squared in the east. Then the slope is -1/2, or -0.5 meters per second squared in the east. Then the next section is the same. It is actually -2/4, which is -0.5 meters per second squared in the east. And finally, the last section is also a horizontal line, or 0 meters per second squared in the east. In terms of the values for this particular case, we can see that most of our values are either just -0.5 or 1. So I'm going to change my scaling for this acceleration. I'm going to leave this as +1 and this as -1. And I think that makes things a little bit easier to draw out. So +0.5 for the first 2 seconds. And then 0 for the next 2 seconds. And then 0.5 for the next 6 seconds. So 1, 2, 3, 4, 5, 6. And for the very last one is 0 again. Good. Connect them using dotted lines. And that is our acceleration time graph. Now we got to do positions, and for the positions, we're going to do the same thing. We're going to find all the displacements between the different time periods. So 2 to 4, displacement from 4 to 6, the displacement from 6 to 10, and displacement 10 to 11. My handwriting is just getting worse and worse as we go. One thing to notice actually, just before I kind of get started in this region for the acceleration, if you notice right away that the acceleration is consistent throughout, you can just go from 4 to 10 and you can skip one of these steps. I'm just doing it for the sake of completion. When I do it personally, I recognize this right away, but just in case you were wondering, if you recognize that the slope is consistent all the way through, then you can just go ahead and skip one of these. But if you're doing the displacement, you do need to include all of them because there will be a different area here than here. One will be positive, one will be negative, and also the size could be different as well. The displacements are found based on the area between the curve and the axis. And the first one, we get a triangle is 1 times 2 divided by 2. So 1 times 2 divided by 2, that's 1 meter in the east direction. I'm not going to worry about, in this case, because it's a graphing question, I'm not going to worry about significant figures. So you have seen that I'm just putting everything in random number of significant figures. That's mainly because I'm just drawing in this case, and I don't need to leave my final answer of what is the displacements or what are the positions at different sections. Okay, for the next one from 2 to 4, my area, I get a rectangle, height is 1, base is 2, that's 2 meters east. And then I get a triangle, height is 1, base is 2, divided by 2 because it's a triangle, 1 meters east. 6 to 10, I have a triangle, base is 4, height is negative 2 divided by 2. That's negative 4 meters east. And finally, I'm just going to change the spacing here. I think they're just too close and also a little bit tilted. It's not straight down. This is 10 to 11. We got a little we got a rectangle. Base is 1, height is negative 2, and that's a total of negative 2 meters in the east direction. Let's graph this. A starting position is 0. After 2 seconds, we move up by 1. After another 2 seconds, or at 4 seconds, we move up by 2 more. After another 2 seconds, we move up by 1. After 4 seconds later, we move down by 4. So 1, 2, 3. Let me just write some numbers here. 3, and then 4. And then after 4 seconds later, we move down by 4. So that gets it back to 0. And finally, after another 1 second, we move down by another 2. So that's negative 2. Okay, let's kind of figure out what we need to do. We can see right away that the the velocity here and here were constant, and because of that, the slope here and the slope, sorry, the line here and the line here will also be straight. And that would mean that basically the slope isn't changing here, and that's why the value is constant. The slope is negative. Actually, the slope is exactly -2, and that's what the velocity here at this point. Okay, now to figure out the rest, at this location and this location, we have a zero velocity. So that would mean it's a straight line and a straight line. And that's enough for us to connect everything. So basically the curve here continues and then it's straight here. And the curve here is kind of like this. So connect this one and connect this one. And we got another beautiful piece of artwork. And that concludes our work in this section. So the first, again, when you're doing these questions, just look for position time, find the proper positions first, then use any constant region of velocity. We'll have constant slope, so that would mean straight lines. Find the 0 points or velocities where it's 0, draw constant lines, and then just connect the lines. So in this case, it starts at a slope of 0 and then bends to here, then straight, and then it bends towards slope of 0, and then from slope of 0 to a negative slope of -2. All right, folks, I hope that this video was helpful and have a wonderful day.